genes and long-term health. Now, this has been shown experimentally in mice. Mice contain a gene called agouti, which makes them obese and yellow and susceptible to diseases like cancer and diabetes. This gene and these traits can be passed down from generation to generation through DNA, so that an agouti mother will give rise to a fat, yellow, disease-susceptible offspring if that offspring contains the agouti gene. Now, here's something interesting about the agouti gene. It can be turned off if silencing epigenetic marks accumulate around it. So, if a pregnant agouti mother is fed a diet which is supplemented with these silencing epigenetic marks, those marks will be chemically transmitted to the DNA of her embryo, where they'll accumulate around that agouti gene and effectively turn it off. Her embryo will maintain those marks, and so it will be born and grow up to be an adult mouse that's thin and brown and healthy. Even though this mother is genetically identical at the DNA level to both sets of these offspring, you can see that the diet that she consumed during her pregnancy can affect the health and appearance of her offspring. Now, this has, of course, implications beyond the mouse world, because studies in humans have shown that women who don't eat well during their pregnancy, who eat bad foods, will go on to have children who are more susceptible to developing obesity and cardiovascular disease. Likewise, if women smoke during their pregnancy, their children will grow up to have a greater chance of developing asthma. These correlations between maternal behavior during pregnancy and the long-term health consequences for their offspring are thought to be linked by epigenetics, much as you've seen here in the case of mice. Now, another important point to make about epigenetics is that these types of marks can be transmitted not only from a pregnant female to her fetus, but also from generation to generation, if the marks are put down on our sperm or eggs. So if you're in the audience and you're not pregnant, and you're not even thinking about conceiving, think about this, because the lifestyle decisions that you make today can still affect future generations. For example, a long-term study was conducted in Sweden and England that showed that young boys who overate or started smoking during their prepubescent years, as their sperm were starting to develop, went on to have sons and grandsons with significantly shorter lifespans. It's believed that the epigenetic marks that were transmitted by their diet and smoking decisions affected the long-term health of their future generations. This type of epigenetic information, of course, can also be passed through females to their daughters and granddaughters if the epigenetic marks are laid down on their eggs. Now, this idea of transgenerational inheritance of epigenetic marks is still being debated and studied in terms of humans, but I should add that non-human organisms, mice, flies, worms, there's mounting evidence that this theory holds true. In fact, it's being shown in the lab that over tens of generations, epigenetic marks can be passed down. Now, another thing to know about epigenetics is that they don't just affect us when we're a developing embryo or when the sperm and egg that conceived us were developing. They can also affect us after our birth. And this is particularly relevant as we think about our brains, which continue to grow and develop throughout our lives. Take this example from rats. Rats contain a gene called the glucocorticoid receptor. And this gene can be expressed or read in a certain region of the rat's brain. And when it is, it helps the rat cope with stressful situations. So the more receptor that a rat has in this region of the brain, the better it will handle stress. Now, there are studies that have shown that interactions between a rat mother and her pups during the first week of their life can have long-term consequences for how much glucocorticoid receptor those pups will grow up to have in their brains, and therefore how well they'll handle stress. This is how this works. When rat pups are born, their glucocorticoid receptor gene is surrounded by a number of these silencing epigenetic marks. This effectively turns the gene off. And yet, if a rat mother extensively licks and grooms her pups, basically takes good care of them during the first week of their life, those epigenetic silencing marks can be removed from the gene. This allows the glucocorticoid receptor gene to turn back on, and it stays on in those pups' brains throughout their lives. So they grow up to be well-adjusted animals who deal well with stress. If a rat mother ignores her pups, that glucocorticoid receptor gene will maintain those silencing epigenetic marks. They won't go away, and they'll stay in those pups' brains throughout their lives. These rats will grow up to be very anxious in stressful situations. This actually brings up a really encouraging point about epigenetics, in that epigenetic marks are reversible. So if you've been sitting in the audience cursing your parents and your grandparents for their poor lifestyle decisions or for the lack of licking and grooming that you received as a baby, take heart. Because scientists are making terrific progress in designing drugs that can reverse toxic epigenetic marks to help combat certain diseases. This is especially looking promising in the case of certain cancers, which happen to be affected or turned on by aberrant epigenetic marks. This is how this can work. Our bodies have certain genes in them called tumor suppressor genes. The job of these genes is to protect cells from becoming cancerous. But if too many silencing epigenetic marks start to accumulate around these genes, the genes get turned off, and they can no longer perform their job of protecting the cell. So scientists have developed drugs which have undergone FDA approval and are in a clinical setting, which can target these silencing marks, effectively removing them from the tumor suppressor genes and allowing these genes to go back to their job of protecting the cell. Now think about it. This is a radical departure from traditional cancer therapy. Historically, we've always been focused on killing cancer cells. This, however, is taking the approach of restoring cells to their original nature, reminding them of what they're supposed to do. This type of therapeutic approach is showing great promise in terms of other diseases as well besides cancer, diseases that are also similarly affected by aberrant epigenetic marks, like diabetes and lupus and asthma, and certain neurological disorders like Huntington's and Alzheimer's diseases. I'm optimistic that this type of therapy is going to hold great promise for our health in the upcoming years, but I should caution that one of the challenges as we go forward is figuring out how to target these drugs toward toxic epigenetic marks while leaving alone the beneficial ones that help maintain our health. I want to conclude by emphasizing that there are things that we can do now to positively influence our epigenome. It's not too late. It's not too late to start eating healthier foods, foods that we already know are good for us, like leafy vegetables, whole grains, avoiding cigarettes, cocaine, stress, all of which have been shown experimentally to impact our epigenomes negatively. These are things that you can do to impact your genes and your long-term health. And if that's not incentive enough, they can also impact the health of your future children and grandchildren. I think this concept that we can positively impact our genes is really profound and empowering, because we'd always worked under the assumption that our genes are set in stone, that they're beyond our influence. I want to end today by challenging you and myself to take the opportunity that we have before us to positively impact our long-term health by treating our epigenome kindly through healthy lifestyle decisions. Thank you.